Hello aspirants. In this module, we are going to see liquid chromatography. Liquid chromatography is one of the chromatographic technique which we have seen already in the previous module. And liquid chromatography is most adopted chromatographic technique in the industry. Especially liquid chromatography is used in the instruments, commonly used instruments in the industry like high pressure liquid chromatography and with mass spectrophotometers. These are the two instruments most widely used in the industrial analytical laboratories. HPLC is having a liquid chromatography system where the mobile phase is passed with high pressure, and liquid chromatography mass spectrophotometer containing a HPLC system along with mass spectrophotometry detector. So this is the difference between the two instruments, and the liquid chromatography technique is adopted in this both the systems, and also the system containing various applications like analysis of various pharmaceutical products, as well as the applications goes into the agricultural sector, chemical sector, and various industrial sectors. We will see how the methods are being developed in this liquid chromatography and the principles of liquid chromatography, and also the applications of liquid chromatography in the upcoming slides. Liquid chromatography, as we have seen the principles in the previous module, it is an analytical technique used to separate a sample into its individual components. You are separating the individual components by using liquid chromatographic technique, and this separations occurs based on the chemical and physical interaction of the sample with the mobile and stationary phase. The principles basically is adsorption and partition coefficient. And what is the chemical interaction and physical interaction? Physical interaction is nothing but the function like adsorption or partition coefficient phenomena. What is chemical interaction? Generally, chemical interaction happens in the ion chromatography kind of techniques where the ions are exchanged. So, the chemical and physical interactions of the sample with the mobile and phase as well as the stationary phase is critical for the separation of the components here. And in case of high performance liquid chromatography, the mobile phase is passed into the column with a high pressure. So the high performance is attained based on the mobile phase which is passing through higher pressure, and also the high end columns are being used in the high performance liquid chromatography, and this separation is based on the affinity of the analyte for both the stationary phase and mobile phase, which is similar to the liquid chromatographic principle. In HPLC, we can have a different kind of HPLC models based on the detector. So we are going to see what kind of detectors used in different HPLC instruments. And by using the HPLC or the liquid chromatography, we can identify the compound, that is qualitative analysis, and also we can estimate the compounds, that is the quantitative analysis. We will be seeing all these things in the upcoming slides. As we have seen, liquid chromatography separate the compound or the sample or a extract or a mix of compounds like formulation or any other matrix into the individual component. You can see when a small volume of liquid sample or a formulation sample injected in the mobile phase, and it is passed through onto a tube packed with porous particles. That is stationary phase, generally a column which is fixed into the liquid chromatographic instrument. So here you can see the separation of three components from the sample with a different retention time. What is retention time? The retention time is the time the compound taken for the elution. For example, the peak number 1 is eluted around zero point 0.6 minutes. Peak number 2 around 0.75 minutes and 3 is around zero point 0.9 minutes. So the differentiation of this elution with different retention time is depending on their affinity for the stationary phase. If it is having stronger affinity, it will elute slowly, and if it is having weaker affinity, it will elute fastly. That we have seen in the previous module also. Now we are going to see the various components of a liquid chromatographic system, or a high performance or high pressure liquid chromatography system, or a HPLC instrument. So the HPLC instrument will having a mobile phase reservoir, which is generally glass bottles, which is kept on the HPLC instrument. Then there will be a pump which will regulate the flow of the mobile phase. So you have to pass the mobile phase with high pressure. It can be done only by a mechanical pump. So a pump is the part of the HPLC instrument. Then there is a degasser which will remove the dissolved gases from the mobile phase. So during the mobile phase preparation and mobile phase storage, this degasser will be used when the instrument is taking the mobile phase from the bottle into the tube. This degasser will be applied to remove the dissolved gases. So the mobile phase will be taken from the bottle through the tube, and the tube will be going inside the degasser and comes out. Then there will be a mobile phase mixing unit also, where different compositions of mobile phase can be, different proportion of mobile phase can be mixed and passed through the instrument. Then there will be a column compartment which holds the column and produces a record temperature for the column. So the column compartment will maintain a temperature which is required for the column, particular column, and it holds the column. Then a auto sampler. So the sample to be analyzed kept in this auto sampler unit, where the injection will come and pick up the sample from the auto sampler unit. The injector unit will automatically come and goes inside the containers which is having the sample in the auto sampler system, and it takes the sample, and it also maintains the temperature for the samples, the entire auto sampler unit. Then there will be an injector which introduce the sample into the column in a appropriate volume. The volume can be set up into the instrument. So according to that, the injector suck the sample from the auto sampler unit and inject into the column. Then there is a detector which detect the sample eluted from the outlet of the column, and generally these detectors are UV detectors, PDA detectors, refractive index detector, and some other detectors, Morse detectors, and other detectors also used. And finally, whatever compounds eluted, the data will be recorded in a data recorder. It is generally a system connected with a supporting software, a computer system connected with a supportive software. So these are all the major components of the high pressure or high performance liquid chromatography system, or a HPLC system. The liquid chromatographic system, or the high pressure liquid chromatography system, can be classified into different types based on the mobile phase, polarity, nature, also the mechanism involved in the chromatography. So now first there are a couple of types of chromatography based on the kind of mobile phase or the polaris nature of the mobile phase what we used in the chromatography. First is the reverse phase chromatography, where a non-polar stationary phase and a polar mobile phase will be used. So non-polar stationary phase and a polar mobile phase. Polar means water or ethanol kind of mobile phases. And in case of normal phase chromatography, it is a polar stationary phase and a non-polar mobile phase. So the polar stationary phase will be having certain compounds in the column, and then non-polar mobile phase means it is generally organic solvents like hexane, chloroform, etc. So reverse phase is nothing but a non-polar stationary phase and a polar mobile phase. This is the most widely used chromatography technique based on the polarity of the mobile phase. And based on the mechanism, it can be again classified into two types, that is ion exchange and size exclusion chromatography. Ion exchange chromatography, the stationary phase contains some ionic groups, for example, sulfonic or tetraalkyl ammonium groups. Then the aqueous mobile phase, generally a buffer. So the column also having certain kind of ionic groups, and the generally mobile phase will be a aqueous buffer. So the analytes what we are going to measure is the ions here, cations or anions. Based on the ions what we are going to measure, the cationic exchange column or anionic exchange column will be used. So basically in case of ion exchange chromatography, we have a column which is having ionic groups, and then the mobile phase is aqueous. Then there will be a cation exchange chromatography as well as anion exchange chromatography based on the analyte what we are going to measure and column what we are choosing. And then finally, based on the mechanism, we can classify the chromatography into one more technique called size exclusion chromatography or gel permeation chromatography. In this technique, molecules are separated depending on their size, which is relative to the pore size of the stationary phase. So the stationary phase will be having the pores, and based on the size of the molecules, the compounds will be separated. The largest molecules will elute first and the smallest molecule elute last. So it is also called as gel filtration or gel permeation chromatography to separate the polymers and proteins, and molecules like hydroxypropyl methylcellulose, carbomers, polymeric materials and other protein molecules are being separated by this kind of technique. So based on the polarity nature of the mobile phase and the stationary phase, we are classifying into two types, that is reverse phase and normal phase chromatography. Then based on the mechanism of the chromatography, we are classifying to another two types, that is ion exchange chromatography, then size exclusion chromatography. Specific to high pressure liquid chromatography, that is HPLC instruments, based on the performance of the instruments, of late classified into two different types, that is one high performance liquid chromatography and ultra performance liquid chromatography. This performance is differentiated based on the pump capacity and the column connections. So the ultra performance is superior than the high performance liquid chromatography. In case of high performance liquid chromatography, we use high pressure to push the solvents through the column. The pump pressure will be maintained at 40 millipascal. And the stream of the mobile phase percolates through the column of the HPLC. Then the components of the sample pass through the column. Then this HPLC allows the analysis of particles having size of around 5 micrometers. The particles which are going to be analyzed should be in the size of 5 micrometers. And the HPLC column internal diameter ranging from 3.9 millimeter to 4.6 millimeter, and the length may be 15 centimeter or 25 or 30 centimeter. And the general flow rate of the mobile phase might be between 1 to 2 ml. So this is the major specifications of the HPLC or high performance liquid chromatography. And in what basis we are going to differentiate HPLC and UPLC? These are the critical factors which is going to be differ from HPLC to UPLC. In case of UPLC, what are the things we will see in the next slide. So coming to the UPLC, the pump pressure of the UPLC will be around 100 millipascal, which will be used to push the mobile phase into the column. And then the high pressure confirms that the whole sample is introduced into the column. Then UPLC allows the particles as small as 2 micrometers, and the column particle size range from 1.7 to 5 micrometer. And the column internal diameter could be 2.1 millimeter or less, and the length may be 10 centimeter or 5 centimeter or lesser. And the general flow rate will be 0.2 ml to 0.7 ml, which is the huge difference between the HPLC and UPLC. You can use the smaller columns, you can use smaller internal diameters, and you can use very low flow rate of the mobile phase in case of UPLC. And the particle size of the analytes could be as low as 2 micrometers. So this is the major advantage of the UPLC systems compared to HPLC system. Now coming to the detectors. What are the types of detectors used in HPLC or UPLC which is associated with the instrument? First is the UV detector, and then photodiode array detector, that is PDA detector, which is most commonly used detectors in HPLC system. Then refractive index detector is also used in the HPLC systems. Then fluorescence detector, then mass detector. Mass detector is the most commonly used detector system because it allows the sensitivity of the method as low as picogram level, and it is used in the general analytical purpose, also in the bioanalytical purpose. And then conductivity detector, which is generally used in the ion chromatography case. And there are detectors like evaporative light scattering detectors, which is used to analyze surfactants kind of materials. Then multi-angle light scattering detector like MALST detectors, which is similar to ELST. This is the schematic representation of a HPLC system, which is demonstrating the different spots and the flow of the entire system. So first it starts with the solvent reservoir or mobile phase containers, which is generally glass bottles. So at a time you can use multiple mobile phase reservoirs. Generally different mobile phases are used. Eventually it will be mixed in a mixing area. So the mobile phase are kept on the above the system in glass bottles, and both will be passed through degassers to remove the dissolved gas from the mobile phase, and it will be pumped into a mixing unit, solvent mixing unit or mobile phase mixing unit. Then the mixed mobile phase goes through the guard column, which is used to increase the life of the critical important column, the other analytical column. So guard columns used to improve the life cycle or life of the analytical column. So the mobile phase pass through the guard column. Then once it pass through the, before passing through the analytical column, the sample will be injected. The sample will be injected along with the mobile phase, goes into the analytical column. Then the is separated into different components, and based on the elution, the components are being detected through the detector, and finally it will be recorded in the computer system. This is how the entire flow of the HPLC happens. This particular slide showing a typical image of HPLC instrument. In this particular instrument, you can see the mobile phase reservoir kept above the instrument, and other parts of the instrument are compactly arranged within this particular setup, and there is a computer system associated with the instrument also shown in the image. So far we have seen the liquid chromatographic techniques with respect to high pressure liquid chromatography, ultra pressure liquid chromatography. Then we have seen types of liquid chromatography in with respect to the mobile phase polarity, and then based on the mechanism we also classified the types of liquid chromatography like size exclusion, ion exchange. Then we have seen the different parts of HPLC instrument and the functions. Now we are going to see how a method can be developed for a particular molecule using a liquid chromatographic system. Before initiating any method development in a liquid chromatographic system, many information need to be collected and understood. First and foremost thing is the physiochemical property of the molecule or analyte what we are going to analyze using the system. For example, if you are going to analyze paracetamol, the solubility of the paracetamol, molecular size, molecular weight, viscosity, pK value, whether it is ionic in nature or a chromophore creating nature need to be understood. Then a literature search need to be conducted if any method is already reported in prior arts. If a method is reported, that method can be taken as a tentative method and further can be developed. Then we need to decide the detector to be used for the proposed method. If the molecule having chromophoric nature, then you can use a UV or PDA detector, and by scanning the molecule in the system, you can fix the wavelength for the detector, either 232 nanometer or 274 nanometer. That will be fixed after scanning the molecule in the system. If the molecule has fluorescence property, then you can use a fluorescent detector for the method. If the molecule doesn't have any chromophoric property or UV absorption or the fluorescence properties, then refractive index detector can be used. The refractive index property of the molecule will be used for the detection. These refractive index detectors can be used for molecules like propylene glycol, glycerol, sugars like glucose and sucrose, polymers like hpmc, carbomers, etc. Then finally, the mass spectrophotometry detector, MS detectors, can be used for the detection as well as the quantification when the sample concentration is very low and you need a very low sensitivity of the method like picograms and femtograms. So in the method development, we have done so far the understanding of the physiochemical properties of the molecule to be analyzed and the chromophoric nature or non-chromophoric nature of the molecule, and we have done the literature search for a tentative method if it is available to develop the method further. And finally, we have selected the detector based on the property of the molecule. Now we are going to do the mobile phase selection. So based on the polarity of the molecule, we can choose between reverse phase or normal phase chromatography. So in case of reverse phase chromatography, the mobile phase will be polar and stationary phase will be non-polar. In case of normal phase, the mobile phase will be non-polar and the stationary phase will be polar in nature. So this selection will be done based on the molecule polarity, and finally a appropriate separation will be obtained by chosen reverse phase or normal phase chromatography. In case of polar mobile phase, we can use aqueous buffers like phosphate, acetate, formate buffers along with solvents like methanol or acetonitrile, which can be mixed together in appropriate composition. To get the resolution between the compounds, the solvent and buffer composition can be varied and selected appropriately during the method development. Further, ion pair salts like alkyl sulfonic acid salts or alkyl ammonium salts can be used to improve the resolution. These ionic samples form a ion pair with ion pair agents in the mobile phase to become electrically neutral. The increase in hydrophobic character of the ion pair results in greater affinity for the reverse stationary phase that lead to better sample resolution. During the mobile phase selection for the particular method development, the following factors can be considered. What are the factors? For the ion chromatography with a conductivity detector, sodium carbonate buffers can be used for anion analysis. In case of cation analysis, reagents like dipicolinic acid, boric acid or tartaric acid can be used for the mobile phase preparation. In case of liquid chromatography connected with mass spectrophotometry detector LCMS, acetate formate ammonium salts only should be used in the mobile phase. Salts like phosphates and halides and sulfates cannot be used for the LCMS methods. And in case of normal phase chromatography, you can use the non-polar solvents like chloroform ethyl acetate hexane for the mobile phase preparation. So these are the certain things you can consider during the mobile phase selection during the method development. So for the method development, we have done the detector selection, the mobile phase selection. Now we are going to do the column selection. What kind of columns can be used for different kind of liquid chromatographic techniques? Silica column or cyano columns can be used for the normal phase chromatography. And in case of reverse phase chromatography, you can use octyl C8 column, octadecyl C18 column, and phenyl-like columns. C18 columns are the most commonly used columns in case of reverse phase chromatography. Anion exchange resin columns can be used for the anion analysis like phosphate, sulfates, and halides. And cation exchange resin columns can be used for the cation analysis like sodium, potassium, calcium, magnesium, etc. For the liquid chromatography with mass spectrophotometry like LCMS, the UPLC columns will be used for the best separation, and always reverse phase chromatography where we use the polar mobile phase is suitable for the liquid chromatography and mass spectrophotometer system. Once we select the column, detector and mobile phase, some more important points we need to consider during the method development in liquid chromatography technique. First and foremost is the diluent selection. The diluent is in which you are taking the standards of the analyte, and the diluent should dissolve the analyte and it should not react with the analyte. This is the most important characteristic which is required for a diluent, and recovery of the analyte is based on your diluent selection. So the diluent what you are selecting is very critical for the method. Then also you have to choose the rinsing solution to avoid the carryover during the method. This rinsing solution will wash the auto sampler injector every time the sample got injected from the auto sampler. Then finally we need to consider and develop a sample preparation techniques depends on the matrix of the sample like tablet, capsule, suspension or some other material. So the sample preparation is based on the recovery process of the analyte. The diluent what we have chosen should dissolve the analyte and able to recover from the drug product. And additional process like sonication, stirring by the vortex mixer or mixers, these kind of techniques will improve the dissolving capacity of the diluent for the particular analyte. In addition to this dissolving capacity or dissolving by additional instrumentation or techniques, you can separate the dissolved analyte by using other techniques like centrifugation and filtration. So basically, the sample preparation, you take the matrix, put it in the diluent, and then you use a mixing process like sonication, stirring, or vortex mixer, or any other mixing process. Then finally, you centrifuge or filter the sample so that you are completely separating the analyte from the sample matrix. So this kind of steps will be optimized during the sample preparation procedure, and this is part of the method development in a liquid chromatography technique. So during method development, you selected the detector, mobile phase, and the column, and the diluent, and the rinsing solution, and some of the sample processing methodology, which includes the selection of additional instrumentation like sonication process or mixing process, and the filtration process or the centrifugation process. So these are the important steps you already considered for the method development. Now you have a tentative method with the selected columns, detectors, mobile phase, diluent, rinsing solution, as well as the sample preparation method. Now you are going to see whether the method is working or not. For that, you need to check several parameters after injecting the sample into the hplc. First and foremost parameter is specificity. Your method should be specific. Now you have taken a matrix which is having x, y, z components, but your interest is only x. You need not to see the y component in your method. For that, you have to prove the specificity of the method. So once you inject the blank, that is the diluent sample, it should not give any peak, and then you inject the standard, you should give the analyte peak. Thereby you are proving the specificity, and you give the mix of the placebo without the analyte, then also you should not get the peak. So you have X, Y, Z components in the sample, but your interest is only the X. When you create a mix of Y and Z without the X, that should not give, the mixture should not give any peak. That is what you are proving in the specificity of the particular method. But when you inject X, it will show the peak, or you inject X, Y, Z, all the three, it should show the peak for the X. So this is what the specificity, your method should be specific. Then second parameter is the recovery. So how much you are separating the analyte from the particular matrix or the drug product. So the drug, for example, 500 mg is added into the drug product. So if you are able to extract or recover entire 100 mg of the drug from the drug product or the matrix, then the percentage recovery will be 100%. So what to prove, how to prove recovery? For that, you have to do the accuracy experiments where you have to take the placebo sample and spike 50 mg, that is 50%, 100 mg or 100%, then 150 mg, 150% of the analyte in the placebo, and then you do the sample processing and show that same 50 mg, 100 mg and 150 mg you are able to recover from the particular sample processing method. Then your method is perfectly all right with respect to the sample processing technique and then the analytical technique. Then the third parameter is the precision. It is the repeatability and reproducibility of the method, that is called precision. So you are injecting 50%, 100%, 150% samples 6 times, means all the 6 times you have to get 50% for the 50 mg samples, 100% for the 100 mg samples, and 150% for the 150 mg samples. And the variation will be minimal so that your precision is very high. So generally the variations will be plus or minus 5% or 2%, depends on the matrix. If you are injecting only the analyte, then it will be 2%. And in most of the pharmaceutical analysis, it is 2%. And in case of complex matrices, it will be 5%. And in case of impurities, it will be more than 15%. So the precision will be demonstrated always with the 100% concentration level, or example, we have taken 100 mg. So you have to do 6 times and see the variations in this particular parameter and see that how much variation is coming, and if it is as low as possible you have to keep, then only your method is highly precise. I think these three parameters has been understood properly now. Then other three critical parameters which you need to verify during the method development is the linearity. So the linearity of the method is the increasing concentration of the analyte should have the increasing analyte response. This is nothing but the explaining of Beer-Lombard's law, where the absorbance of the light is directly proportional to the concentration of the sample or the analyte. So when you inject 50 mg, 100 mg, 150 mg, 200 mg concentration, it will show the increased peak area for increasing order of the concentration. So 50 mg will give, for example, peak area of around 3000. Then 100 mg should give 6000. Then 150 mg should give 9000 and 200 mg will give 12,000 approximately. So that you will get a linearity curve which is having a good correlation coefficient of more than 0.99%. Then your method is perfect. Then the stability, the standard and sample solution shall be stable during the analysis time. So you are injecting the first sample at first minute, and maybe the 20th sample goes after the couple of hours or 6th hour or 7th hour. So the sample analyte stability in the sample is very critical here. During the 7th hour also, whatever concentration initially present, it should same at the 7th hour. It should not degrade or lose during the period. There should not be any loss of analyte. So the stability of solutions should be established during the method development. So you can inject the sample freshly prepared, then you can inject the sample after storing for some time at particular temperature and see the same concentration you're getting both the times. If you are not getting, then the sample is not stable, and how much time it is stable also should be established. Then finally you have limit of quantification and detection, where the method sensitivity is proven. So the limit of quantification is the method in which you are able to establish the minimum concentration you can measure accurately in a particular method. And the detection is minimum concentration you can detect, not quantification. Just detect. That is LOD, limit of detection. And the concentration in which you can quantify properly, it's part of the linearity also, that is called limit of quantification. With this, we have covered the choice of mobile phase, choice of column, choice of detectors, choice of diluent, choice of rinsing solution, and choice of the sample preparation procedure for the method development. And once these all are finalized, then we are verifying the method with the different parameters like specificity, recovery, precision, linearity, and stability, as well as limit of quantification and detection. This comprises an entire method development in a liquid chromatographic method. So aspirants, so far we have seen during a method development using liquid chromatography technique, the critical process selection like detector selection and the mobile phase selection and the column selection are the things what we have seen so far. In case we selected the mass spectrophotometric detector, what are the factors we need to consider and how mass spectrophotometry detector works? So those are the things now we are going to see in the upcoming few slides. So basically the mass spectrophotometric detector is working based on the mass of the molecule. The three different components of the mass spectrophotometric detector are interface and ion source, which is connecting the hplc with the mass detector and creating ionization of the molecule, then quadrupoles, then detector and recorder with software. The molecule mass, that is the parent mass, will be analyzed through the first quadrupole, that is Q1. And the second quadrupole will be used for the generation of daughter ions. And finally, the third quadrupole will detect the ionized parent mass and the daughter mass both. In Q2, if we apply collision energy, then daughter ion mass will be formed and will be detected in the Q3 quadrupole using the mass transition of M by Z. In case we don't apply collision energy, the daughter ion formation will not happen. Generally, collision energy application need to be done during the method development, and it will be optimized during the method development for the generation of daughter ions in case we do the quantification of the certain molecules. In case of qualitative analysis, Q1 based analysis, you need not to apply the collision energy, where the Q1 mass will be generally used for the analysis. The mass spectrophotometric detectors having different probes based on the ionization process. There is ESI probes and APCI probes, and these probes follows different ionization process. First, the ESI probe, it is a process of ionization followed by a evaporation. It occurs in three basic steps. First is the nebulization and charging of the molecules, then dissolution, and finally ionization through ion evaporation. But in case of APCI, it will be reversed. The APCI is a process of evaporation followed by the ionization, and it occurs in two basic steps, that is nebulization and dissolution followed by ionization. So this is the difference between the ESI and APCI probes, and both are adopted for different methods, and which one we need to choose is based on the method development process. The mass transition of the Q1 and Q3 masses will be used for a SIM as well as MRM modes respectively. In case of Q1, we use SIM mode, and in case of Q3 masses, we use MRM modes, depends on the choice of the method. SIM mode is nothing but single ion monitoring, generally adopted for qualitative analysis or identification analysis, and MRM mode is multiple reaction monitoring mode, which is used for quantitative analysis, more specific methods. Optimization of mass parameters need to be done during the tuning of the method. First you tune the method, and we need to then optimize the different mass parameters like collision energy, declustering potential, entrance and exit potential, etc. Specific to liquid chromatography and mass spectrophotometer system, there are different softwares based on the manufacturers are being used. Waters is one of the manufacturer of the lcms systems, uses MassLink software. SciEx is a company manufacture lcms systems, we called as API systems, which use analyst software. Shimatsu also manufacture the lcms instruments, it use lab solutions insight software. Then Agilent, one of the manufacturer of lcms systems, use Moss software for the analysis of various molecules. When it comes to simple HPLC or UPLC systems without mass spectrophotometer, where other detectors like UV, PDA, RI, and conductivity detectors are being used with the HPLC system, several softwares are being adopted in the analytical laboratory based on the manufacturers of the HPLC instruments. Water produces many HPLC instruments, uses the mp4 software. Shimatsu has lab solution insight software. Agilent has Chromeleon software for the HPLC systems. Then Metrum, which produces ion exchange chromatography system, uses the Magic IC software for the conductivity detectors. Now coming to the applications of liquid chromatography in industries, including pharmaceutical or non-pharmaceutical industries, chemical industries, pharmaceutical industries, agriculture industries. That includes the chemical analysis by qualitative and quantitative nature. You can identify the compound, you can quantify the compound in a particular method, adopting liquid chromatography. Then you can do the purity of the products like assay, etc. And then you can do the impurity analysis Then you can prove the reaction completion during the synthesis. Then you can do the byproduct or intermediate product analysis. You can do the residue and solvent analysis. Then you can assess the stability of the product or shelf life of the product can be established using these liquid chromatography methods. Specific to the pharmaceutical applications of the liquid chromatography, that includes analysis of drug and drug products during the various stages of the product development and manufacturing and release of the product. That includes raw material analysis, excipient analysis, intermediate product analysis, finished product analysis, stability sample analysis. And during this analysis, you can do generally the parameters like assay, impurity related substances, dissolution, and extractable and leachable analysis. Finally, we are coming to the calibration part of the liquid chromatography techniques. So instruments need to be calibrated time to time to give accurate results. So for that, to ensure to get the accurate results, what are the different parameters need to be carried out during the calibration of the liquid chromatography systems? The first and foremost parameter is pump flow. For that, accuracy will be measured. Then gradient pump flow, for which also accuracy will be measured. Column temperature need to be maintained properly. For that, calibration will be performed. Then the auto sampler temperature, for the accuracy of the temperature, you have to perform the calibration. System precision need to be done. Then the injection volume linearity need to be done. Whether injection volume is accurate or not, that need to be checked during the calibration. Detector linearity should be also performed. Then the carryover test for the auto sampler also will be performed. Then finally, the wavelength accuracy for UV and PDA detectors will be performed wherever it is applicable. So these are the different parameters need to be performed during the calibration of the liquid chromatography to get accurate results whenever you are using the instrument. So aspirants, in this module, we have seen the liquid chromatographic techniques including the HPLC, UPLC systems, then LCMS systems, then the different parts of HPLC systems. Then we have seen how a method has been developed and what are the important steps need to be followed, important points need to be considered during a method development using the liquid chromatographic system. And then finally, we have seen the applications including pharmaceutical applications of the liquid chromatographic systems and the calibration of the liquid chromatographic systems. With this, we are completing this module about the liquid chromatographic system, and we are going to see the gas chromatographic technique in the next module. Thank you.